Silence. Ladies and gentlemen, today is a very important lesson. Yesterday we talked about indicators of chemical reactions, and we're going to be talking about chemical equations today. And some of you may need to watch today's video, or at least parts of it, over and over again to help you understand some of the concepts. We are going to be dealing with some numbers today, although I don't want you to be freaked out by the numbers. If you can add, subtract, multiply, and divide, those basic math skills will come in handy today and for the remainder of this unit, because what we are going to be discussing today is something that you will be practicing for the rest of this unit on chemistry. So it is a super important topic today. And again, I would encourage some of you to watch it over and over again, as many times as you need to, and to practice. And I'll be providing you plenty of practice this week in particular, but in the future as well, to further enhance your abilities to do what is called balancing equations. But before we get to that, why don't we first talk about what chemical equations are in the first place? A chemical equation is a shorthand for writing a chemical reaction. If you recall, earlier topics, we mentioned the language of chemistry and how the symbols of elements make up the alphabet, and formulas, combinations of those symbols, make up words. Well, today we put those words together to form complete sentences, and we want to make them grammatically correct by making sure we balance them. You'll see what I mean as we go along through this topic, but I've written basic components or parts of all chemical equations. And again, remember that chemical equations are a shorthand for a chemical reaction. They're always reactants, or substances that react with one another, and there are always products, or substances that are produced. And that arrow sign, which we always read as yields, shows the direction in which the chemical reaction is taking place. So in this generalized example, we have various substances reacting with one another, which is why we call them the reactants, and they yield certain substances that are produced, which is why we call them the products. Notice the words I've underlined here, not bad words for you to underline in your notes as you are copying this information down. But the reactants always yield the products. So that's just a generalized description of chemical equations. Let me give you a more specific example. This is one I think you enjoyed in the lab a couple weeks ago, when we took a little piece of this element. Anybody remember what element that is? Magnesium. We took some magnesium and forced it to react with the oxygen in the air by inserting the strip of magnesium metal into a hot Bunsen burner. And the result was a chemical reaction. And think about the indicators we discussed yesterday. Can any of you remember what were the indicators that showed us a chemical reaction was taking place when we put magnesium into the Bunsen burner flame? Yeah, you may remember that really brilliantly bright light. That bright light was released, an indicator of a chemical reaction. And the physical properties of that magnesium also changed from the beginning to the end, because in the end, The things that were produced were not magnesium or oxygen, but rather a compound of magnesium oxide. That white powdery substance that was produced was neither magnesium or oxygen as elements, but rather as a compound. So here's a quick example of a chemical equation that you are somewhat familiar with from previous labs. And, it only involves a few letters and numbers written down. How many of you would rather write it that way as opposed to writing all of the words down? Magnesium metal plus oxygen gas yields magnesium oxide. That's a mouthful, and that would take you a while to write it down. So, again, chemical equation makes it shorter and also makes it clearer, regardless of what language you might speak around the world. Not everyone in the world speaking a different language could understand these words. A chemist or a scientist in any country speaking any language would totally understand the chemical equation. It's a universal language, you might say. So, as we explore this chemical equation a little bit further, it's important for me to point out a law, a very important law called the law of conservation of mass. You see, this is a law that cannot be broken. There are civil laws in our country that you can break, not that you should break them, but it is physically possible to break a civil law. A civil law might be you shall not go faster than 50 miles an hour down the road. That's your speed limit law. Can you go faster than 50 miles an hour? Well, maybe not me in my 1997 Jeep, unless I get out and push it down a hill. But, a car that is capable of going faster than 50 certainly can break the law. There are civil consequences for breaking civil laws, but civil laws can be broken. That's not the case with universal scientific laws. Universal scientific laws cannot be broken. It just can't be done. That's why it's a scientific law. You can't break them. Even if you wanted to, you can't. The law of conservation of mass, again, states that matter cannot be created or destroyed. We mere mortals cannot do that. We cannot create or destroy matter. But we can change the form of that matter. Earlier in the year, we talked about energy, and in a similar way, we talked about how energy, the ability to do work or cause change, is something that can be transferred or transformed from one form to another. But you can't create or destroy energy either. You can't create or destroy matter. We're mere mortals. But we can change it in form. Now, let this sink in for a little while, because this is going to have very important ramifications with our topic today. And I want to start off with a simple example here. I think we can all see this. 2 plus 2 equals something. What does 2 plus 2 equal? Hopefully you don't have to think about it too much before you realize that there is only one correct answer according to the laws of mathematics. And certainly you've all said 2 plus 2 equals 4. That is a law. 2 plus 2 is not equal to anything other than 4. Period. Whether you want it to equal something else or not is irrelevant. It doesn't. It either is right or it's wrong. And that's the way it is in math and in science. So let's illustrate this. If you don't like numbers, let's use food. I love M&Ms, and I especially love peanut M&Ms. So if I have 2 peanut M&Ms in one hand and 2 peanut M&Ms in another hand, and I put them both together, how many peanut M&Ms do I have all together? You might be tempted to say 4, right? No, I'm going to say 0 because they'll all end up in my mouth. No, I'm just kidding. Well, no, I'm not really kidding. They would end up in my mouth, believe me, before I even put them together in one hand. But the point is here that 2 M&Ms and 2 M&Ms together result in 4 M&Ms. Hopefully that's easy. Is this a true statement? Does 2 plus 2 equal 6 M&Ms? You may want it to, I might want it to equal 6 M&Ms because the more M&Ms, the better as far as I'm concerned. But is this a true statement? Hopefully your rational, logical mind is saying, no, that is not true. That is a false statement. And this is how we might illustrate that in mathematics. We would use a symbol that says not equal to. 2 plus 2 is not equal to 6. This is a false statement. Can you write it down? Well, sure, I just did. But is it a true statement? No, it is not. This is a fundamental fact, and it's a very important piece of information that I really need you to grasp before we get into our next slide. So if you're at all confused by what I've just said about 2 plus 2 equaling 4, review your math facts before you proceed. All right, now let's get into balancing equations. Balancing equations is something that we must ensure, that we must do in order to keep the law. And the law we are referring to is the law of conservation of matter, or the law of conservation of mass. We cannot create or destroy matter. 2 plus 2 does not equal 5. 2 plus 2 equals 4. We must illustrate, show, write down true statements. And to elaborate on that, look at the next couple points here. It is the number of atoms, and we'll take this a little bit slow here for a moment. The number of atoms. We know how that's illustrated through the use of subscripts. The number of atoms of each element symbolized by that letter or letters, the symbol of the element. So the number of atoms of each element in the reactant side that we talked about before and the product side in any chemical equation must be equal to one another. You have to have the same number on the left as you have on the right. You must have the same number of atoms in the reactants as you have in the products. It is a law that cannot be violated. Now, the second point here that only coefficients may be altered, we'll get to that. But right now, the main point I want you to get out of this is that you must have the same number of atoms of each element in the reactants that you have in the products. Think of a chemical equation as a mathematical equation. You've got to have the same value on the left as you have on the right. So far, so good? If you get that concept, let's go on to the next slide. So this may look familiar to you. I used it a moment ago. This chemical equation representing the chemical reaction that took place between magnesium and oxygen in the lab, where they were forced to combine together to form a new substance, magnesium oxide. But if you look at this chemical equation closer, you will notice that there is something wrong here. There is something wrong. The way it is written right now is not a true statement. It is not a true equation. This is a false equation. Mg plus O2 does not yield MgO. There's something wrong. And in order to discover whether or not something is wrong in chemistry with a chemical equation, we go through 4 steps. And it's those steps that we're going to be spending the remainder of this period talking about, one step at a time. And it's these steps that I want you to review over and over again to help you not only understand the importance of balancing equations, but also understand how to balance equations. So let's get to it. First thing you do is write down a chemical equation, and here is an example of one. Step one for balancing equations is to identify the elements in the reactants and in the product side of the equation. So let's just do a quick review. These 2 elements here, would they be the reactants or the products? Notice where the yield symbol is. These are the reactants. So if these are the reactants, where's the product? You got it, over here. This is the product. Now I've drawn little green lines in front of each of the pure substances. An element is a pure substance, an element is a pure substance, and this compound, which is a formula for a compound, is a pure substance. I've written lines in the front of there for step 2, which we'll get to in, or step 3, which we'll get to in just a few moments. But first, let's do step 1. Identify the elements. Now, you may or may not have memorized that list of common elements that I've asked you to in the past, but even if you don't know the names of the elements, you can still do this step because you are going to use the symbols. And you can all recognize letters, you can all recognize symbols and the difference between capital and lowercase letters. So on the reactant side of the equation here, the elements that we have are magnesium, and you're going to create a list underneath each side of the equation. So we're going to put in our list magnesium, and the other element that is on the reactant side of the equation, remembering that the yield symbol separates the 2 sides of an equation. So we've listed oxygen. So there are only 2 elements on the reactant side of the equation, magnesium and oxygen. Now we go to the product side of the reaction. And again, remember what this step is asking you to do. It's asking you to identify the elements. Yes, we recognize that this MgO is a compound, but this compound is made of 2 elements. How do you know that? Well, capital M, lowercase g, is the symbol for magnesium. So you write it down. Capital O is the symbol for oxygen. So you write it down. So once you've done that first step, again, you are simply listing the elements on both sides of the equation. You've identified that there are 2 elements on the left, 2 elements on the right. Magnesium and oxygen are in the reactants. Magnesium and oxygen are in the products. You ask yourself the question, have you violated any law in terms of the identity of elements from reactants to products? And the answer is no. You've got magnesium on both sides. You've got oxygen on both sides. So far, so good. But we're not done yet. So let's go to step 2. Step 2 is to count the number of atoms of each element. And I put a little hint there. Look at the subscripts. Use the subscripts to help you. So do you remember subscripts? If not, go back a couple topics and refresh your memory. But the subscripts tell you the number of atoms of any particular element. So let's look at this equation, and we look at each element individually. Is there a subscript there? No, so there's an implied 1. Is there a subscript here? Yeah, it's a 2. Look at the element Mg. Is there a subscript after the Mg? No, so there's an implied 1. And is there a subscript after the O for oxygen? No, so it's an implied 1. So when we tally up the number of atoms of each element, here's what we get. In the reactant side, we've got 1 magnesium and we've got 2 oxygens. On the product side, we've got 1 magnesium, 1 oxygen. So you've done step 2, and you ask yourself the question, have you broken the law in having the equation written this way? And what you need to do is compare each element. We have 1 magnesium on the left. We have 1 magnesium on the right. Does that violate the law? The answer is no, because 1 equals 1. Now let's look at the oxygens. We've got 2 oxygens in the reactant side and only 1 oxygen in the product side. Does this violate the law? Oh yeah. You lawbreaker, you. No, we can't be a lawbreaker in science. We have to find a way to rewrite this equation so that it is a true equation, not a false equation like the one here. So what do? We go to the next step. Step 3. If it is not balanced, which we have seen it is not balanced, the only thing we can do is to change coefficients. Change coefficients. Now remember, I said earlier I put lines in front of the pure substances. Well, I've changed them into boxes, these green boxes, for a reason, because these green boxes in front of each pure substance, whether it's an element or a compound, that is the only place where you can put a coefficient. You cannot put a coefficient in the middle of a chemical formula for a compound. You can't do that. You can't split up the compound that way. You can only put coefficients in front of pure substances. Very important point. Now, by changing coefficients, what you're essentially doing is changing the proportions. Let me use an analogy to help you out. Let's say you're baking chocolate chip cookies in the oven. Before you bake those cookies, you have to put certain ingredients together. Maybe it's a cup of flour, a half a cup of sugar, some oil, a couple eggs, whatever. And don't forget the chocolate chips, for goodness sakes. But you have certain proportions of each in order to make your chocolate chip cookies. Now, is it possible for you to not put any chocolate chips into your chocolate chip cookies? Sure, it's possible. And you could bake those cookies, and the cookies might actually come out tasting pretty good, but are they going to be chocolate chip cookies? The answer is no. You have not made chocolate chip cookies if you didn't put chocolate chips in them. So what you do is you alter the proportions of things. You put the proper amount of chocolate chips in to make chocolate chip cookies. Or what if the recipe called for 2 eggs and you only put 1 egg in? You might be able to bake it, but when your cookies come out of the oven, they're going to be all crumbly and not held together, and they may not even taste that good. Imagine if you only put in half the sugar that you're supposed to put in. The point is, cooking is chemistry, believe it or not, and there are certain proportions that you have to put together. This is what we're talking about when we balance an equation. We have to find the right proportions, and that's what step 3 is all about. If it's not a balanced equation, if the equation we're writing is breaking the law, we have to find the right proportion by changing the coefficient only. So what do? Well, we look at what we have. We look at what we have here. And in the equation, we've got 1 magnesium on the left, 1 magnesium on the right, 1 equals 1. That's okay. But here is where the problem is. We've got 2 oxygens in the reactants and only 1 in the products. So what you need to do is ask yourself the question, on which side of the equation is the smaller number? Comparing the 2 and the 1, which is the smaller number? Hopefully it's clear to you that the 1 is smaller or less than 2. And now comes the math part. You need to think of a number, which will become the coefficient. Think of a number that, if multiplied by 1, will equal 2. What times 1 equals 2? Something times 1 equals 2. What is it? Hopefully, you know that the answer is 2. Well, that answer is what becomes your coefficient in the correct location. You want to go to the side of the equation, the product side of the equation, where 1 is less than 2. And you're going to put a coefficient in front of the pure substance that has the element that you're trying to change the proportion of. And so you do just that. You put a coefficient of 2 in front of the magnesium oxide on the product side of the equation. But there's a phrase I like to say over and over again when we're doing this. Whenever you make a change, you must recount. Say it with me. Whenever you make a change, you must recount. Again, whenever you make a change, you must recount. Because here's the deal. Whenever you make a change by changing a coefficient, if you don't recount, you may not realize that you've altered the proportion of another element. So let's check it out. So on the reactant side of the equation, how many magnesiums do we have? 1. How many oxygens do we have? 2. Now pay attention. On the product side of the equation, we've put a coefficient of 2 in front of the entire pure substance, magnesium oxide. And here's how this counting works. Whatever the coefficient is, you take that and multiply it by each subscript. So magnesium has a subscript of 1. So what is 2 times 1? It's 2. What is 2 times 1? It's 2. So does 2 oxygens equal 2 oxygens? Yeah! So we have balanced this equation. Give yourselves a round of applause. No, that's premature. How many of you noticed that by fixing one dilemma, we created another? We may have fixed the oxygens here, but look at what happened to the magnesiums. Does 1 equal 2? No, it does not. Does this equation break the law? Yes, it does, which means we've got to go on to step 4, which is repeat steps 2 and 3 until it is balanced. So don't get frustrated with balancing equations because it's going to take more than one step in order to complete. So you've got to go through all 4 steps and check your work by recounting every time you make a change, or you're going to be breaking the law with your equation. So what is step 2? Count the number of atoms. We just did that. And if not balanced, change the coefficient. So let's talk about it together here. 2 equals 2 with the oxygen, so we can leave those alone. 1 does not equal 2, so we have a problem with magnesiums. Again, use the same tactic. Go to the side of the equation where the number is lower. Where is the number of magnesiums lower? In the reactant side or the product side of the equation? If you said the reactant side, you're right, because 1 is less than 2. So again, think of a number that if multiplied by 1 will equal 2. What times 1 equals 2? The answer, of course, is 2. And so we place that 2 in front of the magnesium as its new coefficient. And so whenever you make a change, I didn't hear you, let's try it again. Whenever you make a change, you must recount. So let's recount everything. How many magnesiums over here? 2 times 1 is 2. How many oxygens? 1, and by the way, when there's no coefficient, it's an implied 1. So 1 times 2 is 2. How many magnesiums over here? 2 times 1 is 2. How many oxygens? 2 times 1 is 2. So, the $1,000,000 question here is, does 2 magnesiums equal 2 magnesiums? Yes. Does 2 oxygens equal 2 oxygens? The answer is yes. Does this equation, the way it's written with the coefficients here, is that breaking the law? The answer is no. So we now have a balanced equation. So what does this mean? What it means simply is this. It requires, in order for this reaction to take place, and again, think back to chocolate chip cookies, it requires 2 atoms of magnesium added to 2 atoms of oxygen. That is required in order to produce 2 molecules of magnesium oxide. If you have any other proportion, this reaction will not work. So if we put magnesium over something where there's no oxygen, guess what? Without any oxygen, the magnesium is not going to turn into magnesium oxide. This is a balanced equation. So to review, step 1, identify elements. Underline those 2 words in your notes. Identify elements is step 1. Step 2, count the atoms. Count the number of atoms. Underline those words in your notes. Step 3, if not balanced, change coefficients. Underline those words in your notes. Change coefficients. And step 4, repeat until balanced. Underline those words in your notes. Study those steps and apply those steps in examples that I'm going to be providing you for lots and lots of practice. Remember, whenever you make a change, say it nice and loud and proud, even if you're all alone. Whenever you make a change, you must recount. And after each step, ask yourself, have you broken the law? More specifically, does the equation break the law? It is only balanced if you can answer no, it doesn't break the law after all 4 steps. So be sure to review those steps and practice those steps for tomorrow with the following equation. I'm going to leave you with the potential recipe for water. Taking hydrogen and burning it in the presence of oxygen yields water. Your job for tomorrow is to find the correct recipe for this reaction, or in other words, balance this equation for tomorrow. Okay, that is your homework for tomorrow. And so until then, I will say good luck and bye bye.